The final thing I'd like to discuss for chapter 13, and we won't go into great detail on this, is looking at polyatomic molecules. So everything we discussed up to this point has applied specifically to diatomic molecules, but that's a very limited class of molecules. And so a lot of the principles we've talked about still apply to polyatomic molecules, but the details get a little bit more complicated. And that's largely due to the fact that we have three-dimensional shapes, right? So we don't just have two molecules stuck together with a bond. So we'll look specifically at rotations and vibrations. So the main change we have to make with rotations is that we have a molecule, a diatomic molecule can only spin in basically one direction. Whereas for a polyatomic molecule, it depends on the shape of the molecule, right? So if I, grab this random tape dispenser that I have here, this has, which way I spin this will affect how hard it is to spin it. And same thing with molecules. So for rotations for our three-dimensional molecules, we have three different, generally, axes of rotation. And each of those will have its own associated moment of inertia. So we'll have moment of inertia, we label them A, B, and C, IA, IB, and IC. And we by convention, IA is less than or equal to IB is less than or equal to IC. And each of these has an associated rotational constant. So the A rotational constant, for example, in wave numbers is h over 8 pi squared C IA, with an equivalent one for B and C. Well, the only thing that's going to change is this moment of inertia. And so since IA is less than IB is less than IC, that means that A must be greater than, B must be greater than, or equal to. It's possible they can be equal to each other. So these three different axes of rotation, these are the principal axes, and these are sort of the axes that a molecule will naturally rotate about. And we can use these to classify different types of molecules and how they spin. So we have different possibilities. So if all of the moments of inertia are equal to each other, this is known as a spherical top. So this is something like methane or anything that has tetrahedral geometry. If A is bigger than B, but B and C are equal to each other, this is known as a prolate top. So a prolate top is sort of, roughly speaking, cigar-shaped. And this would be something like if we had methane, but with one bromine on it, for example. So we'd have kind of a one axis that's very different than the other two. And then if we have A and B are equal to each other, and C is the one that's different, that's called an oblate top. And this is sort of a pancake shape, roughly. Something like benzene is an oblate top. And then the final possibility is that they're all different. Sorry, and there's no equal sign there. If A is bigger than B is bigger than C, this is what's called an asymmetric top. So there's no symmetry about it. All right. So the energies for these different cases are different from each other. And asymmetric top, this is the biggest class of molecules. My favorite one is isoprene, C5H8. That doesn't have any specific symmetry about it. Okay, so each of these has its own associated energy levels that depend on which type of top it is. So we'll quickly go through these energy descriptions. So for a spherical top, spherical tops are basically like diatomic molecules. In practice, they end up being a lot more difficult to work with in terms of understanding because of all the degeneracies. But there's a quantum number, or there's a rotational constant B, we still have this J times J plus 1 dependence. The main difference is that the degeneracy is the square of what it is for a diatomic molecule, 2J plus 1 squared. All right, for symmetric tops, which is either prolate or oblate tops, we introduce a new quantum number k, which is the angular momentum along the unique axis. So it's kind of like m sub l, but not the same. K can go from 0 to plus or minus 1 to plus or minus 2 to plus or minus j. And we get slightly different equations for prolate and oblate tops. So an oblate top is E equals B, and this is ignoring centrifugal distortion, B times J plus 1 times the difference in C and B times K squared. The degeneracy depends on J and K, and it's 2J plus 1. And then for a prolate top, we get a very similar energy level expression, but now it's the difference between A and B times K squared. Still 2J plus 1 degeneracy. For asymmetric tops, there is not a simple expression that we can write out for the energy levels, and generally we start from the oblate and prolate top energy levels expressions and use those as a basis set to describe our asymmetric tops. So we won't go into the details. Right? If you want to know more, I'm happy to talk to you more about these types of molecules. But there are programs that we can use to model these type of spectra. The one that I'm most familiar with is a program that's freely available, which is really nice, called pGopher. And you can use it to simulate spectra for symmetric tops, for asymmetric tops, spherical tops. It does it all.